And as Rahul already warned us, he may disappear. So we want to finish before that happens. Just in case, was anyone not there yesterday? Oh, no. You're going to be very lost. But I will try for the first few minutes at least to recap a little bit. I don't want to sort of take the entire time to talk about what I talked about yesterday. There was already quite a lot of material covered yesterday. But really the goal of what I'm trying to do is to predict what algorithms do in average case settings when you have high dimensional data and you run a certain set of updates. So the class of updates is hopefully something that's quite generic, things that can be written as sequences of convex programs. So you're interested in solving some sort of ERM problem and computing a solution theta hat, but you really don't get theta hat. You write iterative algorithms to converge to theta hat. The key is, even if this is a non-convex problem, the goal of iterative optimization is you want to frame a sequence of problems that are in themselves tractable. So theta t plus 1 is really given by the minimizer of some loss function, which is typically convex, something that you can truly minimize. This doesn't have to be a first order method. In fact, Vatsal talked quite a bit about second order methods. You can run pretty complicated algorithms as subroutines, as provided you can get to the next step. So the questions that we were interested in yesterday were, if we ran these algorithms in statistical learning, when this data that sits inside the optimization problem is random, should we trust optimization theory? Right? Is there a sense in which worst case guarantees maybe are not as informative as we think they are, right? And that was the motivation for studying these things, and we eventually arrived at a sort of phenomenological tool, which is that of predictions. Can I actually tell you what these algorithms are doing with high probability, not just give you upper bounds on convergence rates, right? So a lot of what Vatsal said actually in the last few minutes is very, in some sense, evocative of what we'd like to be able to do. We'd like to be able to say algorithms are doing these things and then use that phenomenological behavior to make inferences about, literally what's going on iterate by iterate. So this was just a slide from yesterday. So today, I showed you quite a few plots yesterday. I'll show you a few of them today. But the goal today is to actually give you this recipe. So yesterday, hopefully, was the teaser. Hopefully, you saw enough plots that you were like, oh, this guy's doing something. And you thought, okay, maybe this is somewhat interesting. Today, I will convince you that, well, no, I won't convince you. I'll convince you that it's complicated. That's probably what I will convince you. But I will try to tell you what tools are involved in maybe giving you predictions of this form. Again, the key things I'll be using are that each iteration of the algorithm is a convex iteration. In particular, it has a certain saddle type formulation. And that the data matrix in these problems, that is, when you stack up all the x's, this is a Gaussian random matrix. I'll say a little bit later about how these things can be relaxed, perhaps. So we'll try to build this machinery up. I'll start with what I called the sample split setting, where I use different batches of data every iteration. And then I'll move on to the full batch setting, but I'm using the same data every single iteration. Okay, so you'll see the second setting is significantly more complicated, but hopefully you'll learn something one way or another. So I got a few questions yesterday about what it is we were doing. So I'm just going to clarify this straight away. I am thinking of algorithms as taking where I am, theta t, to where I'll go next, theta t plus 1, via an operator, right? And this is a random operator because the data in my problem is random. Now, it's important to understand that I did not show you ways to predict theta t and theta t plus 1. I did not try to tell you how this particular large dimensional vector was evolving across iterations. I was trying to do something much simpler. I was trying to predict errors. However, it's instructive to understand what would happen if you try to understand these thetas in high dimensions. One way to do this is very classical. It goes back to the ODE literature. It's to use the population-based analysis, right? So this is clearly a random operator. It's indexed by n because there are n samples that go into that random operator, n samples of data. Why don't I just take n to infinity and see what happens? Because that's going to give me a prediction of this entire d-dimensional vector, right? So, for instance, this was the problem I flashed to you yesterday. This is alternating projections for phase retrieval. I mean, this will come back. You don't need to really remember these equations for the purposes of today. But the way you should think of, population-based analysis is each iteration itself is an ERM problem. It minimizes some sum of errors, right? So if you have an ERM problem, you will understand how you understand it. You'll understand it by understanding its population limit, by taking n to infinity. So hopefully this average is going to converge to an expectation, and then you're going to be able to understand what's actually going to happen by running one iteration of the algorithm. So let me just be concrete about this. This was the alternating projections algorithm that I wrote down before, but you can already see what will happen when n goes to infinity. Because this matrix, X has identity covariance, that's the identity, right? Even if I invert it, that's an empirical average, it's going to go to its expectation. Okay, so that's the population limit. So when n is infinity, that's precisely the deterministic object that governs where I go next. Okay, this is the population-based analysis. This is not what I'm doing, but this is just to contrast what it is the population gives compared to what it is that I told you we get. Similarly, you could do this with the subgradient method. Just write down the iteration and then take n to infinity, right? Empirical means converge to expectations, bang, right? So when eta is half, if you just look at these two expressions, they're actually the same. And this might be a surprise to you, because effectively we're saying some pretty complicated, very decidedly higher order method has the same performance as the first order method when the sample size is infinite. Okay, and this is one of the reasons why infinite sample size is kind of misleading in these problems, because we don't believe this is true when we run algorithms. So let me just make this concrete. This was precisely the plot I showed you yesterday. I actually showed you these two curves that came from our prediction. Okay, but as you saw on the previous slide, when I set the step size to be half for gradient descent, I can get another prediction, the population prediction from the previous slide, and that's the same for both algorithms. So again, just like these other curves, the population prediction also doesn't require data. You just tell me the first point, I'll tell you what happens next, I'll tell you what happens after that, and so on. So it is a prediction, right? And it's a prediction that goes after the entire d-dimensional object. Therefore, I can compute an error, but it's a misleading prediction. So if I actually ran the algorithms, the population prediction is actually misleading. It's going to mispredict convergence. It's going to tell you faster rates than are actually true. It's not doing what I tried to convince you we can do yesterday. Okay, so this is just to bring everybody on the same page. So what I'm doing is significantly more complicated than a population prediction, especially for those of you who have worked on population predictions. And the key reason this is true is because I'm not trying to go after a d-dimensional object. I'm trying to go after a low-dimensional projection of that d-dimensional object. Okay? All right, so just to make this concrete, in this specific setting, phase retrieval, which is what I started with yesterday, the population prediction will actually predict a quadratic rate of convergence. And I told you already that it's a superlinearly convergent algorithm, the alternating projections with a non-standard exponent. Okay? And it's weird to see a first order method converge quadratically. If you don't believe me, ask Vatsal. Right? And that's precisely what the population prediction will tell you. Right? So that this is really, different in several ways. And that's because we're not just simply taking n to infinity to try to understand what's going on. Correct. So the way to think about it is just purely taking n to infinity doesn't actually account for the finite sample or alternatively the high dimensional correction. Right now we're just doing IID. Yeah. Okay. So just to bring everyone on the same page, let me go back and also just quickly flash this slide. I know it's been a long day, but again, this is going to be a little bit of a running example, at least for the first part of the talk. So it's useful for you to understand what's going on. So that's the phase retrieval model. Okay. Again, it's like the linear model. We just lost a sign. This is the loss that's non-convex that I set up for the model. These are the two algorithms that you just saw. Okay. That's the gradient method for this problem with a step size eta. That's the alternating projections algorithm that sets the sign according to where I am and then executes a least square step to get to where to go next. So that's precisely the two algorithms that I'm thinking about. It's useful to actually think about these two as minimizers of loss functions, right, at each step. More generally, both algorithms have this nice form. They can be written as saddle updates. Okay, so to get, for instance, this alternating projections algorithm, I can just write out a relation. I can just introduce another variable for x theta and then dualize that relation. That will give me precisely this saddle formulation. There are several ways to arrive at saddle formulations. You can also write this squared loss in its sort of Fenchel dual form and you'll get another saddle formulation. So the saddle is something that I'm going to want you to think about. Okay, so saddle updates are a very canonical style of updates and they involve the random matrix X in a very specific way. They also involve some sort of convex concave function, convex in the first argument and concave in the second. Okay, good. So that's the class of things we're going to think about. And as I said last lecture I was going to think about the sample split setting first. Okay, the case where the x's at every iteration are generated afresh, and then towards the latter part of this I'll talk about the truly full batch setting. Yes, you had a question.
For that, the regularizer also has to be convex, right? For that to be convex concave.
If you're interested in how to write this as this, we can talk about it. Yeah, there are several ways to write it, and yeah, there's no regularizer in this particular formulation. If there is a regularizer, it would have to be convex. Absolutely, yes. But if you didn't have a convex regularizer, right, you would not be solving a convex optimization at every step. Okay, good. Yes. Good question. I will tell you, I'll bring them back in just a bit. But in general, you should think of the y's as being partly absorbed in the ux term because the y's have x, right? The y's are generated from x theta star. So they will partly be in this term and they will partly be in this term. So some portion of them will depend on x and some will not. And then you are going to actually split them up. You'll see this very soon. But it's useful to think of this object as existing independently of the y's because it's just clarifying conceptually. I'll show you how to sort of manipulate things such that you can put the y's in both. Yes. U is literally a slack variable. You should think of it as something I introduced. It's a dual variable in the problem, but having this saddle formulation will help us. So I want you to think of the saddle formulation. Eventually, I'm going to be interested in the minimizer here. Yeah. Good. In principle, you could imagine a saddle formulation where you're interested in both the minimizer and the maximizer, right? And we'll get there. Okay, good. So eventually I said I'm going to get after low dimensional projections, and the low dimensional projections I was interested in were this parallel component and this perpendicular component, and I was arguing that, well, as the algorithm converges, it converges on this phase plot. So I literally want to just predict what happens on this phase plot. This is the goal of so-called prediction, right? So what do I want to do? I tell you where I am right now in terms of this low dimensional projection. You tell me where I'll go next. The key is that this is a deterministic prediction that tells me with high probability what's happening with this random variable. All right, so what am I going to do for the rest of this talk? I've been going, I don't know, 15 minutes? Yeah, but maybe for the next half an hour, I'll tell you first how to derive this prediction in the sample split setting. Okay, so in the sample split setting, which is already the plots that you've seen quite a bit, this is already non-trivial. How do we actually go after this type of prediction? And then I'll tell you what changes in the full batch setting. That turns out quite a bit will change, but the sample split setting would provide some clues as to where we're going. All right. So the key is going to be, conceptually speaking, the following. At every step, I'm solving a non-convex problem, but at every step, I'm really constructing a convex surrogate to the non-convex loss, right? And then I'm minimizing this convex surrogate. This is how my optimization is proceeding. This convex surrogate is a saddle problem. It involves the matrix X. And it turns out we have ways of understanding these types of convex optimization problems in high dimensions. They're called M-estimation problems. And there are techniques that exist that allow us to actually go in and analyze these things in and of themselves. Two such techniques are something called the convex Gaussian min-max theorem, which I will talk about. Others are based on random matrix theory and leave one out perturbations. I will not talk about them, but I said yesterday some of our work does use them. So if you want to talk about it, I'm happy to. So let me tell you how one might try to do this. Okay, so I'll try to, let me just describe the convex Gaussian min-max theorem first. So the convex Gaussian min-max theorem is just a purely probability statement. Okay, there's nothing optimization about it. It says the following. Imagine you have two functions. The first of a Gaussian random matrix G, the second of two Gaussian random vectors. The first is the min-max of the following Gaussian process. The second is the min-max of this Gaussian process. So the first is a matrix Gaussian process. The second is a vector Gaussian process. So at this point, these are just random variables. They live in their own probability spaces. the convex Gaussian min-max theorem, more generally, or the older one is called the Gaussian min-max theorem, basically says the following. It says if Q is continuous, then this random variable here and this random variable here are related. In particular, up to a factor 2, the probability that this is small is bounded above by the probability that this is small. This is a very old result. It goes back to Gordon in the 80s. It was used in the escape through the mesh lemma, if you've heard of that. And it requires very few assumptions. Q just needs to be continuous. This needs to be a bilinear form in the random matrix. The convex Gaussian min-max theorem is a strengthening of this, which says if Q is additionally convex concave, not just continuous now, but also convex concave, and this min-max problem is actually over convex sets, in particular strong duality holds in this problem, then the opposite is also true. That is, A is also bounded by P in this stochastic sense. What does that mean? It means if P concentrates about something, then A concentrates about the same thing, and vice versa. Because these are statements on the tails, right? So if these things concentrate, they must concentrate around the same object. So that's the convex Gaussian min-max theorem. It's a very beautiful result. And I'll show you how to use it in the context of what it is we're doing. Okay, you can already see some of these objects look similar to the things that we're trying to control. So how do you actually try to write down a state evolution? You're sample splitting, right? So what does that mean? That means the X matrix that you're dealing with at the current iteration doesn't depend on the U's and the V's so far, or the U's and the thetas so far, right? So that's the key thing that we're going to use, at least for the moment. So this is how you've written down theta t plus 1. Let's just dualize to get to the min-max form we're in. Now, if we try to do this as in an example, let me just use this alternating projections method as the example. That's precisely what you saw a few slides ago. That's my argmin. And I can dualize the squared loss. This goes back to your question, using just a Fenchel conjugate of the squared L2 norm. This can be written precisely as this min-max problem. Okay, this is just the dual of the L2 norm squared. Nothing complicated is going on here. You can verify that this min-max is equal to the min above. Okay. All right. So now to Ankit's question, y does appear in this problem, and y does depend on x. In order to apply the CGMT, which is what I'm going to do next, I need to make sure Q is actually an independent function. I mean, it's a function, sure, but it doesn't have any randomness that G has. Okay, so I have to deal with that, but it's not actually, super complicated to deal with that. I want to apply the convex Gaussian min-max theorem. I have y that sits here that depends on x. What's the obvious thing I should be doing? I should be decoupling the action of y in x, and I should be decoupling things in this term depending on what sits in x and what sits in some sort of orthogonal subspace. So let's be clear about that. In order to deal with this, I have to worry about the fact that x theta t minus 1 appears in this term. I also have to worry about the fact that x theta star appears in y. So let me define a subspace which is the span of those two vectors. This should be theta t, st minus 1, right, is the span of those two vectors. And I'll just write down x theta, I'll write down the first term u x theta as a decomposition across two subspaces. So the first is the projection on the orthogonal complement. The second is the projection onto that subspace. But we know Gaussians behave nicely on orthogonal subspaces. They are completely independent on two orthogonal subspaces. So when I'm applying the CGMT, I'm going to treat this as my bilinear form, and I'm going to treat this as my convex concave function. Okay, so this is already a key thing. At least in the sample split setting, it's kind of obvious. You can imagine in the full batch setting, things are going to get hairier, right? But this is already some sort of key technical thing that's going on when you're applying things. Okay, great. So we have this thing. The CGMT tells us we have a simpler form for this, for precisely this loss. Note, this is a number. It's a random variable. So let me apply the CGMT and take this problem and replace the min-max problem by a min-max problem that doesn't involve a random matrix. In this case, what does that mean? I just take the x thing and replace it here by two vectors, gamma d and gamma n. Gamma d is a Gaussian in d dimensions, gamma n is a Gaussian in n dimensions.
All are independent.
They're all independent. Yeah, in fact, they don't even live on the same probability space. They're just completely independent for now. They're going to soon live on the same probability space. Okay, good. Now, why did I do all this? I claim this is actually a solvable problem. And this might not be obvious immediately, but you just have to stare at this and you realize if I want to implement this maximization inside, I basically have the norm of u that appears in this problem completely independently from the direction of u. So I can separately maximize over the norm of u and the direction of u. Okay, so let me just go ahead and do that. And if you do that, you're going to end up with a minimization problem of this form. Now take my word for it. Okay, I'm not going to go through the gory details of actually doing maximizations and minimizations. If I maximize separately over norms and directions, I'm going to end up with a minimization problem of this form. But then when you look at this again, you can realize that this minimization itself has a similar decomposition, norms and directions. Now you have to be a little careful about which subspace you're considering versus not. But this minimization problem has an equivalent representation in a low dimensional space. So this minimization, which is high dimensional, this theta is a d-dimensional object, is equivalent to this minimization over 3 decision variables.
Then the norms or something.
They have interpretations as the norms of various objects. Okay, so this may have gone fast. I don't expect you to have necessarily absorbed exactly how to do these minimizations, but the key is precisely the state collapse. I went from something that's d-dimensional and effectively wrote it as an optimization problem in very low dimension. What enabled this? What enabled this is the fact that these quantities, things like the projection of a Gaussian vector onto a subspace, they concentrate. They concentrate extremely quickly around deterministic objects. So what I've done here is essentially replaced this term by square root d, for instance, right? And similar other things have happened here that replace this Gaussian norm by something and so on. Okay, so something happened here. In fact, this is an approximate thing, but this is very, very tight. Okay, great. This thing you can just solve. All right, this is an embarrassingly simple problem. You just go ahead and solve it. That omega t, by the way, is a substitute for something that came from the phase retrieval problem. It's this sign of whatever. And you solve this for alpha, mu, and nu. It turns out mu and nu have the interpretation that, you know, mu squared plus nu squared equals this beta squared. Okay? And if you alpha and beta deterministic, then in terms of the previous angle, which I call phi t, this is the precise minimizer of this. And I'm saying, think of mu squared plus nu squared as being beta squared. And I just go ahead and solve this. I won't do the gory thing. But this is a formula, I think we'll all agree. Doesn't look the greatest, but it doesn't look the worst. And in fact, if you Taylor expand these various terms, you will see immediately what the rate is. What is the sine to the 4 Taylor expansion? That's a 4th power of the angle. So if I take the square root of that, right, and this term didn't exist, I would get a quadratic convergence. But this term does exist. It requires some sort of Taylor expansion of the sine here. And if you do this Taylor expansion, you'll realize this is now a cube. Okay? What is the square root of a cube? 3 by 2. That's a formula. Okay? And that's exactly what I claimed. I claimed that this thing converges weirdly with an exponent 3 by 2. In fact, this is the high dimensional correction. If I send n to infinity, this term disappears. I get quadratic convergence. Okay? So hopefully I've convinced you something interesting is going on. And I've hopefully convinced you also that the population is just literally a special case of what just came out. But in the last few minutes, I just completely misled you, because this entire time I've been talking about what? A value, a loss value. And then I suddenly convinced you to believe all these optimization problems. And then I made a claim about the minimizers of a loss from just claiming that the losses are close. Because that's all the CGMP guarantees, that the losses are close. Okay, so that's the last step of this proof. Well, this is what I said just now. The last step is significantly more involved, and I will not talk about it. Even though the CGMT only guarantees that the function values are close at their minimizers, you can actually use growth conditions and then sort of bootstrap this technique on itself and get statements about the not the minimum values but the minimizers. If it's strongly convex, we are almost done. Yeah.
Because CGMT itself will tell us that, like, yeah.
Not quite. You still have to work, but yeah. I mean, if you've done this before, maybe you're talking from a place of knowledge, but you still have to work. So step 4 still requires some work. It's essentially empirical process theory. You have to show that, you know, the supremum of something in a certain set is still well controlled and so on. Okay, good. So this is the sample split setting, and obviously this is something I decided to spend some time on because this is what I spent all the time on yesterday. But as we argued yesterday, you know, people have different moral compasses about what's a reasonable algorithm. And I think this is a reasonable algorithm, at least to develop intuition, but it does involve sample splitting, right? It actually just takes your data and splits it up. And I use this crucially because I use the fact, you know, when I did all these decompositions, or I won't go back to it, but I use the fact that X, right, doesn't depend on the thetas don't depend on X. That X is truly fresh randomness. So how do I actually do full batch? This is actually significantly more complicated, right? And I'll try to tell you a little bit about it. I'm not going to claim that I can really do justice to this, but I'll try to tell you why it is we should expect a low dimensional representation in this set. Okay, so some of what I say will be heuristic, but please forgive me, and we can talk offline if you really have deep questions about why certain things are true. But I will state theorems. So in the state evolution you just saw, there were basically 3 pieces. Okay, first, I had to argue that there is effectively a low dimensional representation, this alpha beta, or what you saw as alpha mu nu, right? So that was part 1. Argue there is a low dimensional representation. Part 2, I have to argue that just because there's a low dimensional representation doesn't mean anything. I have to argue that the actual random variables concentrate around the low dimensional representation. That was the theorem I flashed yesterday. And then piece 3 was actually analyzing the low dimensional representation, which is what we just did. We saw a formula for it. Now for the full batch setting, I'm not going to do piece 3. Piece 3 is complicated, so I'm not going to do piece 3. I'm just going to do piece 1 and 2, at least show you theorems for piece 1 and 2.
For that, why is this different for full batch and split batch? That itself is not.
So maybe I'll answer that just by saying, if we went into this and tried to implement the steps, we already saw we're in trouble here, right? Because this term depended on theta t minus 1 and theta star, right? More generally, what you're going to have is X is going to depend on basically every iterate before it. Over here, X was independent of all these iterates. This is no longer true in the full batch set. Okay, so this is precisely what the AMP state evolution is for instance. It's precisely to decouple this in some sense. Okay, so that's what we're going to have to handle. We're going to have to handle some sort of correlation with the past, and that's just one of the things we're going to have to handle. Okay, good. So another thing I want to point out is that these low dimensional representations, things like alpha and beta, or things like the norm between theta and theta star, these are all what we call pseudo-Lipschitz functions. They're order 2 pseudo-Lipschitz functions. Okay, so if you've never seen this definition before, don't worry about it. It's essentially a Lipschitz function which allows for additional norm growth. But the key thing is that it's a low-dimensional projection, right? It's not, we are interested in predicting a function of our iterates. We're not interested in predicting a d-dimensional object. And this function is a nice function, in particular it's pseudo-Lipschitz. Okay, so here's what I'm going to do for the full batch setting. I'm going to show you 2 generic algorithm families. The saddle will be one of them. The first is actually something that you may know and love and may have seen even before. These are just basically first order updates. Okay, so imagine you generate a sequence UTVT. You just have one random matrix X. This no longer appears new at every iteration, but you just generate UTVT according to this relation. I'm going to adopt a normalization for this part of this talk. I'm just going to normalize the random matrix by 1 over D because it's just more convenient to work with that normalization. That's gradient descent. Okay. And for certain functions f and L, I claim gradient descent can be written in this form. How? Just set ut to be the gradient, and then depending on odd or even iterations, either move or don't move. That's gradient descent. So ft and lt are two functions. They can be time varying. They can depend on the past. So capital U, capital V here are all the past vectors. And I've just written gradient descent in that form. So that's a very canonical way of writing these first order methods. In fact, this has a name already. These are called generalized first order methods. Okay. They involve sort of a primal update, which is a multiplication by x, and they involve a dual update, which is a multiplication by x transpose. And that's all you're tracking over iteration. I appreciate the compliments, as long as they complement. Okay. That's what I'm going to call a first order update for the rest of this talk. I will also consider saddle updates, but this is a specific type of saddle update. Earlier I had a u transpose x theta plus q, which was convex concave. Now I'm going to demand that they separate in the first and the second variable. So I'm going to conveniently write this as a negative function in the u variable and a positive function in the v variable, where each of these is convex. So clearly it's convex concave. Okay, so I'm going to demand some separation. That's, for instance, phase retrieval. But as you pointed out, I think it's the regularized form of phase retrieval. So that's, you can write this as a min-max update. You can write an EM update as a min-max update. You can write a Newton method as a min-max update. You can write many things as a min-max update. We talked about the Prox linear method last time. You can write that as a min-max update. So min-max updates are just very, very canonical. I'm going to require some conditions. I'm going to require that both of these are strongly convex. So it's more amenable to these regularized problems. So the two classes of methods I'm going to prove theorems for today are these types of first order methods with Lipschitz functions f and l and strongly convex functions phi and psi. Again, these can be time dependent. They can truly depend on the previous iterations. This doesn't matter. The key is x is fixed throughout. I draw it once and I still want to be able to make predictions. I also want to note these don't have to be separable functions. For those of you who've worked on AMP type things before, there's a big difference between separable functions and non-separable functions. I don't care. They're just non-separable functions. These don't have to be separable. These don't have to be separable. I don't really care. In lots of canonical applications, they are, but they don't have to be. Another thing that maybe is interesting to those of you who work on these types of problems is often in non-convex optimization, what we do is kind of two-stage algorithms. We initialize with a pretty heavy-hitting method, and then we run a simple method after that. So I am allowing you to interleave these updates. So you can run 5 steps of your second order method and then run a first order method. Or you can run a first order method first and then change to a higher order method. That's perfectly fine. Interleaving is allowed. Okay. So I'm going to try to prove a state evolution for these possibly interleaved updates. The key is I'm not allowing resampling, not allowing sample splitting in my update. Okay. So how am I going to handle general functions? And I should probably speed up a little bit. Yeah, maybe I spend a little bit of time here, but then speed up a little bit when I flash the theorem. So you saw already what I should be doing. I should be trying to use the CGMT, right? Maybe this should be step 1. Already there's a little bit of a, more going on than there was in the previous bit, because these are now general functions, right? I still want a state evolution. Is everything going to collapse in this alpha beta form now? It's not clear. So let me just go ahead and convince you that something is going on and something interesting is indeed going on, even though you don't have this alpha beta type decomposition. You can still apply the CGMT to precisely this problem, right? So this is what this approximation sign means. Okay, so we haven't done anything new yet, but it's not clear immediately how one minimizes or finds the saddle of this problem. In fact, you stare at this problem, it's actually not a convex concave saddle. And I'll let you convince yourself of that. Okay? How does one get a state evolution, or how does one get a low dimensional representation, even if one has written this vector problem? The first thing one should do is just look at KKT conditions, right? That's the first thing you should do when I give you any optimization problem. And these are what the KKT conditions look like actually for this case. Okay? Nothing crazy has gone on. I've just literally taken differentiation with respect to u and v. Now here's the ansatz, and I'm just going to state this. I'm not going to prove it. It turns out that actually these 4 quantities concentrate. This is a non-trivial statement. I'm claiming they concentrate at the min-max value. Okay. So he's going to prove the entire paper while I'm here. So let me, I will not tell you why they concentrate. I'm just going to tell you that they do. It's not obvious, right? Because even for these two, the V and the U depend on the gamma. So it's not immediately clear they should concentrate, but they do. Now, if they concentrate, here's what I can do. I can just replace them with scalars, right? And then I can think of those scalars as giving me my state evolution. They give me my low dimensional representation. So because I'm in non-separable land, right, this is not necessarily just a scalar equation. This is actually a vector equation. Each of these gradients is a vector. I'm going to have to do something a little bit more complicated. I'm going to use HSE to denote some scaled version of this Gaussian in n dimensions. Lambda was n over d, for those of you who still remember. I'm going to use U hat to denote something that lives in the span of U. So it's a scale times U. And that must be equal to the gradient of USE. So just to be clear here, HSE, U hat SE, and U SE are just completely different random variables. They're still random. They just satisfy this KKT system. This is the analogous KKT system for the second one. All right. There is no reason a priori that this even has a solution. Yes. U hat, I'm just saying, is a scaled version of U. This is going to come back. This is a random variable that lives in the span of this random variable. Okay. So that's what you do in one step. So we've handled general functions, right? I'm going to do more than this. Yes. Everything here is a vector. Yeah, everything here is a vector. This is a good question. Why am I going through all this if I have to track vectors in the end? It turns out when it is separable, I only will track scalars. So when things are separable, like it was in the previous example, these will all become scalar equations. But in general, when things are not separable, I have to track vectors. Okay, good. There's a second thing that you probably didn't notice, which is that actually these things are all related to each other if they concentrate. In particular, the L2 norm of this is a scaled version of the L2 norm of V, right? Because the Gaussian just concentrates in L2 norm. Similarly, the L2 norm of this is a scaled version of the L2 norm of U. And then you get other relations depending on U hat. If I put all those relations together, this is what I end up with. So what is my state evolution? It's random variables that satisfy this system and this system. This may look complicated, but trust me, this is actually just a slightly more complicated way of writing what it is I wrote in terms of alpha and beta. So let's just look at this, for instance. So I said this is HSE. I'm just claiming the norm of this, the squared norm of this, because this Gaussian concentrates, is precisely the squared norm of this. That's what I've written. I'm just claiming that the norm of gamma n, it is apparent simply because the norm of a, even look at this. There's no, gamma d is a Gaussian in d dimensions. What is its norm? Root d with high probability. So I'm just claiming that this thing, if I take its norm, or the expectation of the squared norm of this thing is going to literally be the expectation of the squared norm of U. So it's not, it may not be immediate if you just saw these equations, but it doesn't take long to see this. Okay, great. So I've figured out one step of this thing. I've just gone a small little way. The second part of this, which I will not spend any time on, is actually handling coupling with history. Okay, so this is where we have to be much more careful with how we do this decomposition. So earlier we were decoupling only by projecting onto this span thing, theta star and theta t minus 1. Now I have to project out span of all the v's and span of all the u's. For all t before little t. Okay, this is called Bolthausen's conditioning. All right, it's not a terrible thing to do. You should think of this as t as being small still, right? So the key thing here is that this object is completely independent of this object. Because these are just projections onto orthonormal subspaces, you can represent, and this is the non-trivial portion, this particular inner product can be represented purely in terms of the past SE quantities. Okay, I will not give you a proof now, you can catch me later if you're interested. And the reason for this is simple. If you look at this in a product and you try to repeat the KKT argument from before, these two are the terms that will appear. Okay? And it turns out that these two things, just by this concentration thing that I argued previously, are representable in terms of the U's, V's, and the SE quantities from before. Okay? Quite a bit more has to go into proving this. But now I have an iterative CGMT. This is not a one-shot CGMT, but an iterative CGMT. So what you do is just write the KKT conditions. You use the fact that U hat is in the span, V hat is in the span, and then these quantities GT and HT. So the key now is, unlike the one-step CGMT, these GTs, HTs, and SE quantities are actually coupled. They're on the same probability space as X. And they're evolving as your iterations are evolving. So let me write down the state evolution. So this is the Wolthausen conditioning argument. I mean, it's in some sense a souping up of the Wolthausen conditioning argument, but it should be attributed to these two papers here. Just phenomenal papers on literally led to the AMP as it is. But this is going well beyond the AMP. So how do I write the state evolution? Again, for instance, you might want to track inner products between iterates, right? That's a low dimensional function. So how would I track inner products between iterates? Or in general, how would I track a pseudo-Lipschitz function of all my iterates? I will track them using these SE quantities. So how would I do that? I'll stack up all the G's, so as columns of the capital GSE matrix, and similarly the capital HSE matrix. They're all Gaussians. So the only thing that matters is second order statistics of these objects. So imagine I just have IID rows and I capture their second order statistics by these KG, KH matrices. Lambda, again, just to remind you, is n by d. This is the state evolution. It's a complicated object. It's going to take me a slide to describe, but this is how the state evolution behaves. Just literally, these are three state evolution matrices that you're building up iteratively in V space and U space, with V hats and U hats that lie in the span. You initialize these SE random variables according to how your iterates themselves look. That's how they start. And then you just do the same sort of iterative update that you saw a few slides ago. If you have a saddle update, this is precisely the equation I wrote down. For the first order update, the equation looks a little bit different. And how do you fix all the coefficients? Because at the end of the day, U hat is something in the span. You need coefficients to determine something in the span. You fix coefficients via those expectation relations that you saw a few slides ago. This looks super complicated. And it's not simple by any means. It's just something that takes work. But the important thing to understand is that these are all low dimensional objects. Every single thing here is a low dimensional integral that you can compute like that. Okay? So there are two questions that I'm left with. I shouldn't take too much longer than this. I'll speed up. So the first thing is, everything you see here is a function of a Gaussian random variable. The one thing I swept under the rug is that a solution to this may not even exist. Right? This is some weird thing I just made up. I wrote down a bunch of KKT conditions and I said, okay, this must be true. There's no reason a solution to this should exist. And the important thing to note is that these are all very low dimensional things. Right? So if you truly have a separable problem, you can compute all these quantities extremely quick. If you have worked on the AMP before, this is a reparameterization of the AMP state evolution. If you worked on the Gordon CGMT before, this is a reparameterization of the Gordon state evolution and so on. So there are two questions, and I'll flash two very quick theorems. A, did I make everything up? Is there indeed a unique solution to the system I wrote down? And B, this is just a deterministic prediction. Does it actually reflect what's happening when I run these full batch updates? The answer to both is yes. The answer to both is affirmative. So first of all, this system that I defined a few slides ago, there's a unique law that's consistent with that system. This is actually new. It's new even for AMP with, as far as I know, the G forms, the first order updates without separable functions. And I want to say that, this is, I'll just say proof technique here is interesting because it actually is a proof technique in Hilbert space. It takes this entire problem, takes it to infinite dimensions via lifting, and then argues via duality in infinite dimensions. So this is an interesting proof technique pioneered by a couple of these papers, but it sort of generalizes it to non-separable updates. And the answer to 2, is this deterministic prediction useful? and this is the theorem, you take any order 2 pseudo-Lipschitz function of your iterates. This can be anything. This can be an estimation error, a generalization error, an inner product. I don't care. And then you take that same order 2 pseudo-Lipschitz function and you apply it to the SE random variable with an expectation. So this is what I'm saying is a low dimensional integration. This is a faithful prediction at the 1 over root n rate. But unfortunately, in our general saddle problem, we pay in this disgusting 2 to the minus t if there are t saddle updates. Okay, so I believe this is loose. But one thing to say is that if you have purely first order updates like you do in AMP or gradient descent, you can actually improve this to the 1 over root n rate. This 1 over root n rate is tight. So what does this use? It actually uses a completely different proof technique as far as I'm aware. It's a proof technique that's independently interesting. It just uses the fact that various objects in here are in themselves order 2 pseudo-Lipschitz functions. And then there's a new concentration inequality for order 2 pseudo-Lipschitz functions.
There should be some sort of convergence of measures or something.
Good question. Does this imply any convergence immediately? The answer is not quite. One thing that does imply convergence is if I could take a supremum over all order 2 pseudo-Lipschitz functions, this would imply convergence in Wasserstein. But as written, it does not. I believe convergence in Wasserstein is also true. Okay, so let me end. This is just taking way too long. So the general takeaway is you can do these, full batch things in addition to doing the sample split setting. Again, if you were satisfied with the sample split setting, your takeaway might just be, hey, look, this is a giant algebra problem, right? It's not, what it really is it's taking a giant algebra problem and simplifying it into a much lower dimensional algebra problem that you can actually execute very quickly. The key things we used were Gaussianity and this sort of convexity every iteration. I won't say much about stuff that is upcoming, but I will leave you with a couple of open questions. There is sharper concentration. That's a technical question. This 2 to the minus t, I don't believe should appear. We can relax. I'm sure what we're assuming on saddle updates, we're currently assuming strong convexity, separability. I'm sure that's not necessary. You can ask questions of the flavor we kind of asked yesterday, which is, if I'm going to run a saddle update for my problem, how should I choose my functions? So this is a very nice class of questions about optimality within a class of algorithms. This can be rigorously posed given the state evolution. Last thing I'll say is these predictions appear to be universal. We ourselves do not have theorems that say this, but just to give you an idea, imagine you actually plot the predictions assuming you have Gaussian data, but now you run the problem where the matrix X is replaced with Rademacher IID random variable. I would argue that's agreement. Okay, so universality is known to be true under some conditions, and it's not true in the general setting that I talked about. But I believe this is a very nice direction more generally. And I'll leave you with this question, which is, hopefully you saw things here that reminded you that you like some algorithms that you would really like to understand in the average case, even if you didn't understand all the details. But really the question I want you to walk away with is, can this machinery say something about your favorite algorithm? And if it does, then I'm happy to chat about it. All right, thanks.
Question to the topic.
There are two of them.
Oh, sorry. Yeah, I thought it is a bit heavier than usual.